And then second of all, the chat is going to be disabled, and additionally, you won't be able to turn on your camera or I think that's it, actually. Turn on your camera, just so we can keep the presentation going. But like Lewis said, if you have any questions during the presentation, feel free to ask. Um, and we will try and get to them as much as we can. And I did mention it already, but we do have two upcoming programs. The tour of a house built with ICFs, which should be pretty interesting, coming up next week. It's in Fairfield, and then we also have our annual birthday benefit fundraiser coming up in December, which you're able to get tickets to. Our members, of course, get discounts, so be sure to become a member if you're interested in discounted pricing. And additionally, just to answer the first question that's in the chat already, we will be sending the will we be sending the PowerPoint presentation around up to attendees afterwards? Is that possible?
I
The
can look, yeah, I'll take a look
Okay,
with Rockwell Corporate, and as
great,
long as I get a yes, we'll send it.
great.
I know you'll have a recording. Do you typically share the recording?
Exactly. Yes, we do. Yeah.
Okay.
So that'll at
Well, if
least
one way or another,
one
people,
way or
yeah,
another, yeah. Whether you take screenshots of the recording or something,
that's it.
it'll
Yeah.
be available. Okay, and that's all I have, so I think I'll hand it over to Holly.
Awesome. Thanks, Kate. Good afternoon, everyone. Thank you so much for joining us today. My name is Holly Havel, and I'm with ICF. We are the vendor working on behalf of the sponsors of Energize Connecticut to bring this Passive House and All Electric Homes training series to you. So these trainings are at no cost, thanks to the sponsors of Energize Connecticut, and are part of a partnership with Connecticut Passive House and Build Green Connecticut. As we mentioned, today's training will be recorded and posted online afterwards. Also, a reminder that as part of this training and workforce development initiative, we offer a 75% cost reimbursement for individuals pursuing either FIAS or PHI professional accreditation. So this includes the cost of the training and the exam, and the reimbursement will be processed upon successful completion. If you have any questions about the reimbursement process, please contact us at the email on the slide. Next slide, please. So in addition to this no-cost educational training series, as well as the professional accreditation reimbursements, the sponsors of Energize Connecticut also offer robust incentives for builders and developers who are pursuing all electric with their residential buildings or pursuing Passive House certification in multifamily projects with 5 or more units. The Passive House incentive design includes pre-construction incentives for feasibility studies and energy modeling, and post-construction incentives that range up to $60,000 for full Passive House certification. Next slide, please. So the all-electric incentive is for both single-family and multifamily buildings. It offers 2 levels of eligibility with specific design and performance requirements associated with each, and has incentive amounts ranging from $1,500 per unit for multifamily up to $10,000 for single-family homes. So our goal is for everyone involved in the construction of residential buildings in the state of Connecticut to be aware of these incentives. If you're interested in learning more, please visit our website or contact us at the number on the slide. So during today's session, please feel free to use the Zoom Q&A feature to communicate questions or comments to the presenters. And also a reminder that today's session is approved for AIA and GBCI CEUs. So with that, I'd like to introduce today's speaker. So Lewis Smith is the Business Development Manager for Rockwell in the US Northeast. He works closely with architects, contractors, and builders to address challenging construction details, navigate evolving energy codes, and achieve high-performance building outcomes. So with that, take it away, Lewis.
Holly, thank you. Thank you very much. So I'm excited to be here. It's interesting, I don't often present here from the home office, and I'm blessed to have that opportunity today. I'm typically on the road. You could find me on a job site with the belt on. I help coach installers who are learning how to do high performance construction for the first time with some of the more challenging details. And my background also extends to the architects. So this is an AIA accredited presentation that we're going to be serving today. This is called Stone Wool Insulation, Understanding Stone Wool Insulation in Exterior Wall in Rain Screen Applications. So if I were in your architect firm, this would be one of a few of the presentations that we have available for AIA. If you're interested in more information about what I do and what I can do to help with your construction projects or designs, feel free to reach out to me. I'm going to go ahead and ask Holly and the Greenbuild CT team to share my contact info with everybody after the call. So the learning objectives in this presentation is to discuss the thermal properties and energy efficiency benefits of stone wool versus foam plastics and other products, and most particularly focused on the rain screen and cavity wall systems. So these are high performance systems. Code is going to be calling for exterior continuous insulation in 3 of the 4 prescriptive code options now as of 2024. Examine how stone wool manages moisture as it relates to rain screen and cavity wall systems. These are heavy moisture loaded systems. Your walls, your roof, it's all applicable, and moisture can be one of the primary causes for even litigation in the building industry. So moisture damage, mold, rot, and decay, those are things that plague our buildings. A lot of people who have worked the industry for years have seen these, and it's hard to escape it. We have learned as an industry community, we've learned best building practices, how to mitigate these things. We're going to discuss how stone wool can help contribute to the drying of a wall system. We're going to describe the features and benefits of stone wool in the context of building science and fire safety. We're going to summarize some of the environmental and sustainable aspects of stone wool as well. And just as a quick announcement, we will have LEED credits available. We have LEED documentation on our website. So let's break down the basics of different types of insulation. We can categorize these under 2 primary tiers. There are fibrous and vapor open products. These products could be what's listed on the slide, your fiberglass, stone wool, slag wool, it's cellulose, but it extends beyond that, right? We've seen hemp material come into the market. We've seen everything down to straw houses. We've also seen denim material, right? And genuine sheep's wool used. So there are a lot of different fibrous materials, and they share one primary characteristic, right? Is that they're vapor open. Vapor open materials can help facilitate the drying of a wall assembly. Depending on the climate zone, will need to be used in conjunction with a vapor retarding layer of some kind. This will be called out by code. Foam plastics is the other tier. Foam plastics can tend to be vapor closed. This will be primarily determined by the thickness of the foam, but as little as 1 inch can be considered vapor closed depending on the type of foam being used. So we have an extruded polystyrene XPS, expanded polystyrene EPS, polyisosanurate, and polyurethane. These will range in R value between approximately R4 per inch and R6 or 7 per inch, depending on the type of foam plastic being used. What is stone wool? Stone wool is produced from natural and abundant basalt rock. This is basalt. It's a volcanic stone. It's one of the most abundant resources in the world today. You dig down far enough and more or less you're going to hit the volcanic layer of the Earth's crust, right? So recycled slag can be used as well to manufacture a stone or a mineral wool. And slag is a byproduct from the smelting of iron ore. What does that look like? You melt down iron ore and mineral impurities separate from the pure iron. And during that process, the mineral impurities tend to float. They float to the top. They are scraped away and discarded. And there are only few use cases for that waste material today. Manufacturing of insulation is one. The wool is then spun blown, and we do that in our factories by heating up the stone until it's effectively lava. So we've created a high heat, high intensity manufacturing process. The lava is spun and wisped into small fibers. These fibers are much like cotton candy, but they don't taste as good, I promise. Then the material is going to be layered and compressed into a variety of forms and densities. In general building insulation today, we manufacture both bats and boards. Binders are added for both rigidity and water repellency. The process, the manufacturing process, is fairly circular. We go as far as using stone wool as the filter medium in the chimneys in our factories. We filter the impurities out of the air. Using our stone wool, those same filters are crushed and reground and made into more stone wool insulation. So there's a lot that we can do during the manufacturing process to keep this a green, more healthy process. Rock wool today in the manufacturing process tends to overachieve the metric set by the mineral wool manufacturing process for total embodied carbon. We're going to look at total home solutions. Where is stone wool used in a building? Continuous insulation here on the left-hand side can be utilized not just on the wall system, but also below grade. The presence of moisture does not affect the fibers in stone wool. They do not degrade or deteriorate in the presence of moisture. It's an excellent product for below grade use. And it can also be used in this exterior continuous application up the roof line where I'm showing the mouse here. You can see my cursor on the screen. Fire and soundproofing is a very common application area. You'll see this in floor systems and wall systems, demising walls, especially when we look at multifamily units. This is crucial to keep the occupants in a quiet and comfortable environment, but also protect them in the instance of fire and mitigate the spread of fire between systems. Thermal bat insulation is commonly used here in attic systems and exterior wall systems. You've got the party wall here between units again, and it's worth mentioning that not just below grade against a foundation wall for the boards, but we can also use boards sub slab. And we manufacture, there's a board, stone wool board that's manufactured with the compressive strength needed to handle the load of a slab. Features and benefits of stone wool. The primary is fire resistance. Every fiber in stone wool is stone fiber. That means it's 100% non-combustible fibrous material that's used. It can melt, but it cannot burn. And based on the purity of the stone, the basalt, and the other stone mix, the blend that's being used, you can achieve incredibly high melting points, well over 2000 degrees Fahrenheit. This is a look at the Grenfell fire. This was in, of course, Grenfell. It was June 14th of 2017. This fire had an exterior insulated system completely wrapped in foam plastic. The foam plastic was found to be not just combustible, but had an incredible smoke development. And there were, unfortunately, many casualties due to this fire. It was a 1,000-home housing complex. There's a Netflix documentary out about this now. If you want to learn more about what happened, you're able to find that. So how does flame and smoke development pertain to some of the different products that we've looked at here? Stone wool. At the top left, you can see an ASTM E84 testing showed 0 flame spread and 0 smoke development. Smoke is the #1 killer in a fire. Smoke inhalation, even above and beyond the burn. Fiberglass had some flame spread, less than 25 feet, and smoke development of less than 50 parts per million. So this has a lower melting point, which you can see here on the chart on the right. You've got your stone wool melting point, which is well over 2000 degrees. Fiberglass is going to melt with a shorter duration of time and a much lower temperature. Okay, so the fibers are not as dense or robust as stone fibers. Then much below that, we've got a couple of different foam plastics that were tested, polyurethane foam and polystyrene foam, which both melt and burn respectively. So these are important things when we're considering the safety of the occupants in the event of a fire. NFPA 285 is a test that's conducted to determine the assembly's resistance to flame spread from one story up to the next. Okay, so can we contain flames in a floor without letting it spread up to the floor above? So a failure in this test would be the flames crawling up the wall system. It's important to note here that this test is not strictly of one product alone. Okay, so this isn't just stone wool that's being tested or foam that's being tested. This is a full system test. And a lot of the testing that stone wool currently today is subject to, and a lot of building materials are subject to, are full systems tests. It's important to mention that the heart of the system, the heart of the fire safety system, is going to be the stone wool, and the rest of it is equally as important. So what other materials we choose, whether or not they are combustible, all those factors are going to impact the overall performance of a system when we test for things like the NFPA 285. This is an interesting slide. I'm going to let it roll for just a moment, and then I'm going to pause it here. Okay. So what we see is we see on the top half a wall system that was designed to mimic an exterior wall with exterior continuous insulation. So remember, code is going to start calling now for exterior continuous insulation in 3 of the 4 prescriptive code options. If we're utilizing it, how is the building impacted in the presence of fire? On the interior cavity of the top of this slide, you can see it's a standard sheetrock detail. We've got a standard fiberglass insulation in an open attic. So this is all very standard construction. At the base of the wall, the firefighter here ignites a propane fueled fire. To reach failure point in this test, flames need to spread up the wall system and reach the attic where the house would be consumed. There's a lot of fuel for a fire in an attic assembly. There's a lot of oxygen, right? And fire needs 3 things. It needs fuel, heat, and air. If the fire reaches the attic, I think it's a common conception that the house is considered nearly a total loss, if not a total loss, because the fire can spread and be so devastating here in the attic system. So at the bottom of the slide, underneath this cladding system, this is vinyl siding. Instead of XPS foam, we have stone wool. And we're going to see with a propane fueled fire that simulates a grill fire, will the flames spread up the wall system to the attic and reach failure point? Stone wool has already passed 1 minute in this test, where XPS has passed only 2 seconds. This is because the stone wool does reach the full 30-minute duration of this test. And unfortunately, the XPS wall failed at 3. So the stone wool timer is moving quick. Now, if I was live in front of a real audience, typically at this point, I mention the smoke development on the bottom slide. Why do we see smoke, right? And the audience tends to gravitate to the idea that the vinyl siding is melting into this propane fueled fire. It's releasing smoke. We understand that stone wool does not emit smoke in the presence of fire. So this cannot be a smoke development caused by the stone wool in this assembly. Here, stone wool has reached 12 minutes. XPS is at about 1.5 minutes. The vinyl siding on the stone wool portion has nearly burned back as far as it can from the heat of the flame. The smoke development has begun to subside. But at 2 minutes, the XPS wall is beginning to show signs of the flame spreading. And for me, when I look at this, I just imagine, I light my grill, I go in the house, I'm getting plates and burgers and dogs and maybe a quick drink. And it's amazing how fast things can change from bad to worse. So we're going to see at 2 minutes and 50 seconds, smoke development in the attic just before it hits a flash point. Attic is consumed, and the firefighters have to extinguish this fire. So this test failed. on XPS was unfortunately fuel for that fire. It is petroleum based. A lot of these foam plastic materials are petroleum based, which acts as a fuel for fire. Here at the bottom, we see at 30 minutes, the fire was extinguished and the test was passed. Okay, so we're going to move on to the next slide. And we're going to talk about sound absorbency. This is a second staple for stone wool insulation, is sound absorbency. We recognize that life is loud, and frankly, things seem to be getting louder. Whether or not it's an open concept home with more large, echoing, galley style living, you've got large kitchens and dining areas. And so what can we do? Noise is traveling further. The appliances are always running. There are plastic pipes in the home. You can hear toilets flush. And then, of course, kids are gaming with their headset on, saying things we don't want to hear, and the television's running. Stone wool has the ability to achieve a very high density. Stone wool can be 3 to 4 times more dense than a typical glass fiber bat. And that gives us an excellent sound absorbency. We hit excellent STC ratings. We're going to talk about STC ratings, but we can even make stone boards, sound boards out of stone wool here. These are commonly used in movie theater rooms or home offices or music rooms. And so what is a sound transmission class, an STC? Architects can frequently specify these STC rated assemblies. In some commercial construction, STC ratings are required. I was working a project recently where we needed to achieve an STC rating of 55 for the partition wall between 2 units. Okay, we were able to do that. We used a double stud system there. But an STC rating is a snapshot. It's designed to measure what would be the sound frequency range of people talking. Okay, so this range is between 125 and 4,000 hertz, and it's effectively if I oversimplify it, it's effectively a measurement of decibels stopped from passage through an assembly. Okay, so an STC rating of 55 would be essentially 55 decibels blocked through the assembly. Decibels are a rating that measures on a curve. Okay, so about every 6 to 10 decibels is what we perceive as an audible doubling of the sound. Okay, so if you imagine that going from an STC rating of, say, 40 to 20, you're not halving the sound there. You're nearly cutting the sound in half 3 times. Okay, at that. So the STC rating is important, but it's not the full picture, because there are sound ranges below 125 hertz, and these are more common when we look at buildings and areas with high traffic in the environment. So near a busy street in a city, traffic sounds can run regularly below 125 hertz, and that is where the stone wool insulation really performs. It can outperform at the high density of stone wool by over 25% what a typical glass fiber bat can handle. So here on the next slide, we're going to look at more on the high density of the stone wool bats. Stone wool bats are very high density, again, like we've discussed. This means they cannot sag and slump in a wall cavity over time. This becomes really important when we work with residential or remodeling contractors. They pull the sheetrock off the wall and find the state of the insulation behind is terrible, and it's sagged in the wall, leaving uninsulated cavities in that wall. And this isn't just important for sound. This is important for thermal control too. When you have uninsulated space, you're losing the thermal performance of that cavity. And even a small uninsulated space like you're seeing here in the picture on the left, this can equate to a massive loss in thermal performance, especially in the heating season, where heat rises and exits out of the top of the system. Stone wool in this image here on the left-hand side, the large image, this is installed in a roof system over a typical I-joist. The bats are so robust, they just hold themselves in place. They're free floating above these hat channels that are installed for the sheetrock attachment. That friction fit will last a lifetime. Stone wool has been tested now. We've got product that we're testing over in Denmark that's over 70 years old, showing the same original structural integrity and same original R value. And this speaks to long-term thermal resistance. Stone wool achieves its R value like other fibrous insulation does by trapping pockets of air within the fibrous matrix of the material. Okay. And so with that, we can achieve with stone wool between R 4.2 and 4.3 per inch. And that is a stable R value that shows 0 decrease over time. Compare that to some of the foam plastics that are commonly used, like a polyisocyanurate, which can have a higher R value, 5.6 in year 1. But this is not trapping air. This polyiso is going to use a blowing agent trapped within the pockets of the foam plastic. That blowing agent can hold a higher R value per inch initially before the foam plastic begins to deteriorate. Plastics break down, we know, over time, and that particular material can see as much as a 20% decrease in performance in years 2 to 20. Extruded polystyrene also will see a decrease in performance from an R5 to an R4.5. These are not industry secrets. This data is based on the manufacturer's warranties from these products. Okay, so it's important to recognize when you're selecting a product, is it performing to the extent that you think it is years, 5, 6, 7, 8, 9, 10, or are we building and expecting that year 1 performance is going to last? R value is a common metric that all insulation material is measured against, okay? But R value is measured and tested at 75 degrees Fahrenheit. So I'm going to show my cursor over this part of the screen. You can see 75 degrees Fahrenheit, and we have in red a stone wool cavity insulation at 4.3 per inch. Now, this is standard for our stone wool products. Unfortunately, at 75 degrees Fahrenheit, you just don't need insulation. Okay, right? You could effectively open a window and let the air flow, keep your AC off. Everybody's comfortable. Where it counts is when it's cold. So on this chart, as we draw left, the temperature is decreasing and the R value is slightly increasing. The stone wool cavity line jumped from 4.3 per inch to 4.82 per inch now. Why? Well, with the fibrous matrix trapping air and achieving R value based on trapped air within the product, we know cold air, 25-degree air, is a higher density, therefore trapping more of the precious air that achieves R value within the fiber structure, increasing the R value of the material. Compare that again back to the polyisocyanurate, this foam, which has a higher R value at 75 degrees. Unfortunately, that R value decreases as the temperature decreases. So this test data is really important for people who are selecting insulation in a cold climate, right? Somewhere where we're heating for the majority of the year. How is the insulation performing? Not just year 1 to year 2, but from 75 degrees to 25 degrees, right? When it really counts. Stone wool insulation can be flexible, although we do manufacture a rigid board. It offers some forgiveness for architectural designs with things like a curve. So semi-rigid stone wool can offer you a curved aesthetic for some of the more intricate design details. We've got a host of different projects that the stone wool was curved on, and we also offer a design guide to help show how much we can curve depending on the thickness of the material. So encouraging the architects to reach out if you have some more intricate designs. Dimensional stability. This is really key. Now we're moving into the exterior wall systems. Dimensional stability is going to become a key consideration when you're looking at exterior continuous insulation. Continuous being the sense that you're wrapping outside of the sheathing layer of the wall system an insulation that is not obstructed by framing. Okay. So in your cavity, you have studs and you have cavity insulation, and those studs are thermally conductive. We'll look at some of that here in a bit. Heat can pass through the thermally conductive studs. They're more conductive than the insulation. Studs hold roughly an R value of 1 per inch. Okay, so compare that to a stone wool, which would offer an R23 in a 2x6 wall. A stud in a 2x6 wall is only going to offer about an R5.5. Okay, and so we use exterior continuous insulation to give us a 100% return on the insulation R value added to the exterior of the building, because it is not obstructed, it's not broken, it's continuous. And the continuity of the insulation is really contingent on its ability to resist expansion and contraction. When insulation contracts, you have airspace, cavities for heat loss around the panels. So let's look at performance. In this test, there was a 122 degree temperature swing across a 33-foot span of board. So figure that this is the average temperature swing from a hot summer day in New England to a cold winter night in New England, right? We have stone wool across that 33-foot span showed an expansion or contraction rate of only 1/10 of an inch. This was half the movement concrete experienced in the same test. And personally, I love this stuff. I thought that was really impressive. Steel shared with concrete a similar expansion rate. Expanded polystyrene moved 1.4 inches. Extruded polystyrene moved 1.6. And polyisosanurate at 2.4 inches. And so if you're doing some quick math, let's say a 32-foot span, right, is divisible by 8. How many panels are sharing this nearly 2.5 inch contraction? And how much uninsulated space is around these panels? I'll show you what it looks like. On this slide, there's a roof system with polyisosanurate foam. This would be a flat roof. This picture is really particularly impressive because we can see the heat loss around every single panel here. I can see exactly where the panels are. And if you were remediating like maybe a water leak on this, you have perfect access to exactly where the panels are and all the fasteners on each panel. You could see exactly how this system was installed. So the heat loss in this system on the flat roof was tremendous in the cold weather. When you have heat loss like this, you also have areas that are more vulnerable to moisture condensation, okay, moisture condensation risk. And so there's a host of other problems that this issue creates, okay? That is exactly the thermal bridging that the exterior continuous insulation was trying to control. We were trying to mitigate thermal bridging with exterior continuous insulation and can't effectively do it because this particular product shrunk when it was cold, okay? Water repellency. At the beginning of the presentation, I talked about it briefly, that water is the #1 cause for litigation in the building industry today. Stone wool is hydrophobic. You're going to see in this picture that the water just beads up and sits on top. You could practice it. If you had a sample of stone wool, you could pour water right on it like that. But when held underwater, stone wool saw that it could drain and dry effectively as well. And so not only is it water resistive to moisture on the surface, but it drains and dries, and that's partially what makes stone wool such an effective insulator subgrade. The fiber is unaffected by wet and dry cycles. So it'll both create an effective drainage plane in an exterior rain screen system, but it will also drain and dry subgrade. This is an example of submersion. So the material was held underwater, under a 5-inch head of water. And after this test, after 1 minute, it had absorbed an average volume of 3.69. So this was pulled out, removed. 3.69% of the water volume it absorbed was remaining. After 15 minutes, it began to drain and dry. 60 minutes, and 12 hours to 0%. So this creates a really effective drainage plane. It can also help facilitate drainage again, not just within the fiber structure for a rain screen system, but subgrade, helping to improve the performance of water drainage around a foundation. It is vapor permeable. Stone wool is vapor permeable. So this is important to identify the difference between moisture vapor and air barriers. So moisture vapor barriers and air barriers are two different things. These are often confused. I'll use the image here on the left to show the two. So the blue layer here, this would be your WRB. So think something like Zip System or Tyvek, right? Typar, there's a host of different materials that could be used as a weather resistive barrier here. These are going to create your primary air barrier around the system. They are also your primary water, well, it's a secondary water barrier to your cladding, but this is the building's last line of defense to air and water. But this layer is vapor open. So one of the requirements for a WRB is that it does need, in our climate up here in Connecticut, it needs to be vapor open and help allow drying should water accidentally get into the cavity. But in our climate, on the interior, you can see this. This is a depiction of a vapor retarding layer. So you can think like craft paper or polyplastic or even a smart vapor membrane. Code will call those out as reactive vapor membranes. And this is designed to stop moisture vapor from coming into the wall system from the occupied living space within the home. So the trick here is a good wall system should never include two vapor barriers. One needs to be a vapor barrier in our climate, and one needs to be vapor open, allowing moisture to dry away from the building. Okay, so we're always trying, and this would be true whether you're a roofer or a sider or you're a carpenter doing flashings. You're always installing your materials in such a way that the water will drain away from the building, right? We don't install shingles, right? Top layer first and then the bottom layer where water can get in underneath the adjacent shingle. We layer at the bottom and shingle above, facilitating water runoff that way. The same strategy applies when we're thinking about moisture vapor. We want the vapor to diffuse out away from the building system, keeping this dry, okay? Stone wool insulation is going to average about 30 perms. This is very high. This is higher, much higher than your typical wall sheathing will be. So any moisture that is interacting through the sheathing is guaranteed to dry out through the insulation here. This is not vapor restrictive. And so here we have a depiction of an excellent wall system. Reducing the amount of moisture vapor in a wall system is going to reduce the likelihood of mold growth, and it's also going to reduce the likelihood of rot. So keeping that system really dry, really well ventilated, right? Or not so much ventilated, but really well vapor open. So in high performance buildings where we have exterior continuous insulation, we run the risk of utilizing a vapor closed material here that is going to prevent outward drying. And then we would rely on interior drying, okay? The dew point is a critical issue in the wall assembly. So the dew point, you can think of a cold glass of whatever your favorite drink is, iced water, lemonade, you name it. You're sitting at a bar. When you look at your cold glass, there's moisture condensation on the glass, but it's not actively raining in the building you're sitting in, right? So you have moisture in the air around you, but it's not at 100% relative humidity all around you. It is at 100% relative humidity where it condenses on the glass. And so at 100% relative humidity, we hit what's called the dew point. And dew or moisture will condense on the first condensing surface in the wall system. This is often the sheathing or the framing of the studs, okay? Utilizing exterior continuous insulation can also be, with the right ratios, a strategy to move dew point effectively outside of the wall system. If you were to do that, okay, and so you can always contact Rockwool. We have a great technical team. You could contact myself. We can move the dew point outside of the wall system and eliminate the need for interior vapor control, therefore allowing for free drying in either direction and eliminating the risk of moisture condensation on all the vulnerable parts of this system. Your vulnerable wood sheathing, your vulnerable wood framing, keeping that system effectively drier than we've historically ever built, right? So unless it was the old homes with no insulation and pine board siding, right, and air just blowing through the whole system. This is the best way that we can mitigate the moisture risk is by using the proper type and amount of insulation in that system. Potential drying
Louis,
issues.
sorry, I think we had a question just about the the illustration in that slide, if you wanted to go back.
Talk to me.
They were
Yeah,
just asking, what is the outer green layer?
here. That outer green layer is just a simulation of a cladding system. So imagine if it were like a commercial system and we had metal wall panels on the outside, right? So here you see metal framing, metal stud, and then this would be like a non-combustible exterior sheathing. So this is a typical illustration of commercial construction. For people who are building residents, I would say just pretend in your mind's eye that that's a clapboard.
Great, thank you.
Yep. Sorry for glazing over that. Yeah, it's an odd, that is an odd pick. I would agree. But not my slides. I'm just presenting. So here we've got a potential issue with the depiction here. This is a cold climate system, so think how we build in Connecticut, right? But we've got XPS, a vapor closed foam here on the outside, and then again a vapor retarding layer on the inside. This has two vapor retarding layers, and the great building scientist, Dr. Joe Stiebrook, has a way to describe this that I probably can't say on a recorded wall, but he calls it a sandwich, a crap sandwich, more or less, is what he says. And it's because with two vapor barriers, we're trapping water inside that system should it eventually make its way through. And how would water get in there? I mean, if everything was built perfectly always, it wouldn't, right? But the reality is, we aren't building perfect every single time. It's nearly impossible to duplicate a perfect wall system in every single building. And not so much as construction errors, but occupants. We can't control the occupants. Somebody's going to come through here and they're going to hang a picture on the wall, pierce that precious vapor retarding layer, and allow for moisture to come into that wall system. Walls can see moisture from outlets, electrical outlets, and light switches if they're not properly sealed. This system could potentially have a high risk of water intrusion. And there was something interesting that came up recently in a presentation we were doing for Studio HPDC. A family of four can generate as much as 4 gallons of water a day from bathing, cooking, even breathing, right? And so when we look at the areas that are important to the occupants of a home, it's usually the bathroom, the kitchen, right? And so we can't stop an occupant from cooking and bathing. We wouldn't want to. And you certainly wouldn't want to stop them from breathing. So moisture will be in the conditioned space of this environment in the winter when moisture is trying to drive out. So if we understand how moisture drive works, moisture drive is going to push from high content to low content, much like heat. Heat will travel from the hot portion to the cooler portion, right? Heat is driving that way. Moisture drives in a similar fashion. So in the cold climate months and the cold winter months here in Connecticut, the warmer, more moisture laden air inside the occupied space is always trying to push outward through the wall system towards the cooler, drier air outside. Okay. And so in a system like this, if there were vulnerabilities in the interior vapor control layer and you have a completely vapor closed exterior, you get this trap. And in this system, we have a greater wetting potential than we have drying potential. And this would be, and again, I'm going to pretend these are wood studs because my life is spent mostly with wood frame construction. We would have water trapped in these vulnerable areas of the home. Okay. So let's keep it moving. Here we're looking at that hideous green cladding again, but what we want to take away from this is, what would a system with an excellent drying potential look like? We've got an interior vapor control layer. This should be a reactive vapor membrane if we have the budget to afford it. A stone wool high density batt insulation, which is going to give us fire safety, sound, long-term thermal resistance. We've got an exterior, they show an exterior gypsum board. This is, of course, commercial construction. You could supplement this for anything that we would typically see in residential construction if you're a residential designer or builder. Vapor permeable air barrier. So again, we're differentiating between the vapor permeable portions of the system and the vapor impermeable portions of the system. We have stone wool semi-rigid board insulation. This will give you your continuous thermal control. This gives us a rain screen. It gives us a vapor open measure and additional sound attenuation in the exterior wall. And then we've got that exterior cladding. And I'm just going to go ahead and pretend it's a clapboard because that's, you know, back to the preference, right? So drying potential, why is drying potential so critical? This was from a WUFI analysis over a 3-year period in climate zone 4. So this is taken right out of New York, New York. Seasonally, there are changes. Now we see this, we experience this, right? Especially when I had a rainstorm come through my house last night. We got a tremendous amount of rain. The ground is still muddy and wet around my house. The fall can be a wet season. Okay. We have lower temperatures. It's not, the ground isn't drying out as fast. The environment is not drying as fast in the fall. This will also hold true in the spring when we experience a great deal of snow melt early on, right? March, the snow's melting. April, right? April showers. We get a lot of rain. So you're going to have seasonally these spikes in this chart here. These spikes are high moisture load that your wall system is trying to manage. So how much moisture is the wall system trying to manage? And again, we've got it here, fall, spring, right? Some in the summer, back to the fall again, big spikes. But the drying potential is the majority of the year. So these valleys in this chart are low, very low water content in the system. So this is a system that's going to experience periodic spikes of high wetting potential, but an increased season of drying potential. And that's giving the system the ability to dry thoroughly, reducing the risk of rot and mold growth. Okay. So our goal is always to achieve a system that has a balance where the drying potential is continuously greater than the wetting potential. In a high performance rain screen system, we look for stable long-term thermal resistance, vapor permeable systems, fire resistant, moisture resistant, excellent sound absorbency, and something that's environmentally sustainable. Okay, so here's some look at what this exterior system might look like on a more traditional wood frame construction home. We've got traditional clapboard siding. These furring strips are here to give us ventilation behind the cladding. This is going to improve the finish of the cladding, the durability of the finish, allowing for drying both outboard and inboard of that system. It's going to give us a drainage plane for any accidental moisture that makes it in between gaps and cracks in the system. And of course, we have our continuous insulation, giving us a thermal barrier against the thermal bridge that all the framing introduces here. So even the header over the window has great insulation over the top of it. We know there's probably stud packs here, right? That are transferring load. These are going to be well insulated on the exterior where we can't insulate well on the interior of the building. One last note here on performance of a stone wool. This is less prevalent here in Connecticut, but we tested termite resistance. There was a 28-day exposure test with 400 Formosan termites, and we were evaluated to be termite resistant with stone wool. The reality is this, right? Untreated wood is something that wood-boring insects like. Maybe we don't have termites in Connecticut. We do have carpenter ants in Connecticut. We do have carpenter wasps. There's all kinds of things that eat wood up here in Connecticut. And this image in the middle of the bottom right is what it looks like when wood boring insects get into wood, right? Treated wood had the second highest weight loss in this test. So untreated wood had an incredible amount. Treated wood also had the highest mortality rate for termites. Stone wool, however, showed an excellent visual rating after the test. It showed the lowest amount of weight loss. It was actually found in this test that the termites buried the stone wool in sand, which is odd behavior, but it's a behavior that they exhibit when they find an undesirable food source. So the point of this, I think, to show is more relevant that the stone wool is insect resistant. For anybody who's done remodeling work and pulled off old insulation that is not insect resistant, you can see exactly how much havoc these wood boring insects can wreak on things like foam-based insulation products that might not have the same insect resistance as a stone wool can. Here we show ICCES certified applications tested, and so we've got several tested and rated assemblies. If you're interested in any of those, never hesitate to reach out. And that concludes the presentation. So we're just on time, and hopefully can allow for some more questions. I haven't been looking at the Q&A or the chat. But if anybody wants to chime in, I'm happy to hang out for a few minutes and answer the questions you have.
Yeah, great. Thank you so much. That was super informative. There were two questions that have come up so far. One of them was during the presentation. It said, how is the thermal performance of the below grade fibrous insulation maintained if it becomes wet?
Yeah, good question. So you have to remember that there's an incredible drying potential in this product, right? And so if you have temporary exposure to water, okay, and the water will be forced. So I think the question is based on the idea that water is forced into the fibrous structure through hydrostatic pressure, right? You put the insulation underground, water is forced into the fibrous structure of the material, and then you lose the R value performance because it's moisture laden. And to an extent, that would be correct. But it drains and dries so quickly that you would not experience long-term loss of thermal performance during water exposure because you're facilitating the drying around your foundation wall utilizing the stone wool. If you know you're building in an area with a high water table, you're going to want to take additional measures for water management around your foundation. So you can install just stone wool against the foundation wall and backfill against it. That's completely acceptable. In areas with a high water table, it's going to be recommended to do the stone wool and then a dimple mat to increase drainage potential in that area, along with a free draining backfill. So if it's known that we're building in an area with a high water table, we do take additional measures to make sure we're facilitating the draining. Those would be often used in conjunction with a French drain system or perimeter drain system around that foundation. So not only are we allowing the water to dry down, like to drain down, but we're also giving it an avenue of escape from the foundation. So as long as the effective drainage measures are taken, the insulation cannot hold water long term. And you will maintain the thermal performance without seeing degradation of the fiber due to the presence of water. So hopefully that helped.
Yeah, that's great. Thank you. There's a few more questions that have come in.
Awesome. Keep them
yeah,
coming. Let's go.
Great. Keep them coming. In your view, how comfortable are builders nowadays with installing exterior continuous insulation?
Okay, that's a good question. It depends a lot on the experience of the carpenter, right? So I've been working now just over a year in the field hands-on with installers. It's been really interesting. You know, I talked to some guys and they're so hesitant about I feel like the installers who struggle, they struggle more with the mind block than the actual practice of installing insulation. You know, it's the what ifs that kill a guy, and they get so caught up in these things that it slows them down, and then they get on and they're already so nervous. that they struggle. I spoke with a guy, his name is Steve Raposa, and he's a builder for Silva Brothers up in Newton, Mass. So Silva Brothers, like HGTV, this old house, Silva Brothers, he builds for them, and he did 4 inches of exterior continuous comfort board on a project where I asked him, hey, what challenges did you hit, or where'd you get hung up, and were you able to get the strapping straight? So because that's the big thing is you want to make sure your siding is straight and all your trim and everything lines up right. The aesthetic is what the customer's buying more than the performance. So he said, no, it's no problem at all. I said, what'd you do? And he said, I used a clutch drill instead of an impact. And he adjusted the clutch so he wasn't over compressing material. And he went. I've got tons of pictures and videos. He let me interview him on a couple of videos, and he talks about his experience. So, again, it's more of like the experience. Here's a guy. He told me that he grew up without impact drivers, just drills. So he was like, I mean, this guy's got wrists of steel, right? He's running just a drill, and it was really cool. So I would say, how comfortable are people with the concept and installing it? It depends on the experience of the contractor, and if they can get over the mental block, they're going to do great. But that's, it's one of those things. So I see, I serve 9 states today, from New Jersey, Pennsylvania, and north, and I see a mix of confidence. The areas where guys are the most confident are Massachusetts, New Hampshire, Maine. They're really confident. They've been doing it longer up there. In the Jersey market, in New York City, it's a lot harder to find somebody with the same confidence level. But yeah, so hope that helps. Well, you
Yeah,
can always call on me, right? Like I'm a resource and I talk to these people all the time. So, bring me out to your job site. We'll train the team, get them all up to speed and shorten the learning curve, right? That's my job.
yeah, that's awesome. Is there a email we can send out to folks? An
Yeah,
email?
should I put it in the chat? Do you want
Yeah,
to send
sure.
it? How do
Absolutely.
you want to do
Because
it?
that's fine. I can also send it in the follow-up
Yeah,
emails, people's AIA credits as well.
I'll
Um,
put it in the chat for now. And then if you want to add it to the follow-up, yeah, I'm happy to let people
Perfect.
get a hold of me anytime. The
Awesome.
trick with my email is it's lewis.m.smith, because ironically, I'm not the only Lewis Smith at Rockwool. We're a global company. There's another one of me in the UK. So you gotta see, are you sending it to me or the guy in Europe? You know?
Perfect. And yeah, I mean, that's a lot of the times as, like a building nonprofit in the sustainability space, we hear a lot of like, oh, well, this is just how it's always been done. And like it works because it's been doing, we've been doing it that way. So, it works, but that's obviously not the case. And I think it's a great testament to kind of like working with people and moving forward for the best.
Well, yeah, and some of the times, right? I was so impressed with that guy Steve because he's an old school guy and he's
Hmm.
done things for a long time, but I don't see him as one of those people that ever got set in his ways, like stuck,
Hmm.
you know?
Yeah.
And the building materials have all changed now. We're using different types of siding. Like where was cement board siding 20 years ago? Where
Hmm.
was engineered wood siding 20 years ago? Where were some of these flashings and tapes and wraps and insulation products that we never saw 20 years ago? So if we're building the same way today that we built 20 years ago and we're using all different materials,
Hmm.
is it going to work?
Be right. Yeah.
You know?
Yeah, absolutely. We had few more questions. The first was, what is the byproduct of melted stone wool?
The byproduct of melted stone wool. All right, so I'm going to give this my best a
Mhm.
go, but maybe whoever asked can clarify in case I'm missing the mark here.
Yeah, sure. Jan, if you want to clarify, I can unmute you.
So we melt stone wool and you get melted rock, like um
Well, what is the
right.
characteristic is the question that I have. Is it a puddle? Does it become a plastic surface? Does it become a rock in and of itself?
Oh, it basically turns into obsidian. I actually have a piece. If you ever want to check it out, let's get lunch sometime. I'll bring you. I've got some pieces of rock I could show you.
Great.
But yeah, you melt it down and it looks like obsidian. It looks like glass, black glass.
Very interesting.
But
you.
we look to spin it into fibers before letting it, harden in that state. We typically, even when the factory is shut down, we often keep the furnace running, so that we never hit that state. It can be really time consuming to clear a clog, if you could imagine how bad that could get.
And nothing just about the melted rock wool.
Yeah, so I feel like I'm missing the mark here. We melt the rock wool and we just get molten rock again. So in theory, it's infinitely recyclable. That's why we're able to use the filter cartridges are made out of stone wool. They look a lot like comfort board. When I was doing a factory tour, I walked past a stack of those filter cartridges and I was shocked. Like, they look like comfort board. I saw them and pointed to them and saw the label was filters. And I was like, oh, that's kind of cool, They will melt that down and make more rock wool out of it. And so waste material off our lines is again melted down and made into more insulation. The lines, as much as possible, we try not to ever shut them down, continue producing insulation.
Thank you.
Yeah, yeah. And if again, Jan, if I miss the mark on that, just shoot me an email or give me a call, maybe I can help get into more details.
You got it. I appreciate it.
Awesome. The next question was, how well does the stone wool keep its shape against the backfill weight on the foundation? Does it compress significantly?
Oh, it's a good question. No, it doesn't compress significantly, we perform really well, and we have different densities for the boards. So comfort board, the one most commonly used subgrade, is the same one we use in the exterior wall and typical sloped roof. So this is called comfort board 80. It references an 8 pound per cubic foot density. It gives us a compressive strength at 10% compression of nearly 490 pounds per square foot, which is more than enough for the load of your typical slab or your backfill. But we've tested it up to 25% compression to show over 1,000 pounds a square foot of compressive strength. So we're going to do really well there for you. That's a non-concern. We do make an 11-pound density comfort board. It's a little bit more money. It's more fiber in it, but that's 11 pounds per cubic foot, and that's called comfort board 110. It's typically used in commercial applications that would have a thicker, heavier slab, or a requirement for a higher density panel to hold different cladding systems, higher, heavier cladding systems. So we don't often see that, if ever, in residential construction.
Great. Thank you.
Yep.
And can you talk about hybrid applications, for example, minimum layer of closed cell spray foam on the underside of roof sheathing with stone wall bats in between roof rafters? Do you recommend that method or not?
Oh, that's a good question. Okay, so this becomes a hot roof, right? Where typically it's hard to maintain ventilation space when you're doing the flash and baff. I have seen a few people put the baffles in to try and allow for ventilation, then foam it over the baffles, and then install rock wool. I've got an excellent installer down in New Jersey. Their top to bottom insulation, and they do a ton of the flash and bat style install, this hybrid system with a first layer of spray foam. they're using the rock wool in that assembly to help facilitate drying inwards towards the building. Should moisture get into that cavity, and they're utilizing the rock wool as a fire barrier to help protect the combustible spray foam that they're using in that assembly. Do I like it? You know, it's not my favorite system because you're putting a vapor closed layer, right? And so now we kind of get into my opinion when part of the question is, do I like it, right? And I've seen too many failures in foam, delaminating from framing, delaminating from sheathing, and that can happen if the moisture content of the building is wrong during the install, or the mix of the foam is wrong, or the temperature that it was sprayed was wrong, right? So there's so many factors to making a perfect spray foam application, and people who use it are counting on not just the R value, but usually the air and the vapor barrier as well, and like a closed cell foam. And I feel so hesitant on something that's so fragile in overall performance. So when you ask, do I like it? Flash and Bat's not my preferred. I like to rely on a dedicated air barrier, a dedicated, I like my control layers as more dedicated parts of the system. And then I can know, like, okay, this is doing what it should. And, typically you don't have the same fragile install commitments. Like, when you're installing rock wool, for example, you just stuff it in and walk away. So yeah, so I guess part of the question is what do I think about it for a roof? Like, can it be done? Yes. How do I feel about it? It's not my favorite. But if you're gonna do it, I think you should adhere to Dr. Joe Steebrook's ratios. Rockwool will offer these as well. But the ratios are for mitigating condensation risk. So you have a vapor closed layer right up against your roof. Typically in Connecticut, you need about 40% in climate zone 5. 40% of the total roof system insulation should be spray foam. And then you no longer need interior vapor control, and you can allow the vapor to dry back into the building. That would be how I would do it. If I was going to do spray foam in a roof system, 40% of the total insulation should be spray foam, and then we no longer have a need for interior vapor control. That would be your best performing system, but you're holding your breath and your fingers are crossed that foam doesn't fail down the road.
That's great. Thank you. Very insightful. And then I think these are the last two questions we have so far. From the same person, so they might be related, but what thickness do you recommend for exterior insulations? Do you recommend window bucks? And then would you need to use long screws to go through the insulation to the studs to attach the siding?
These are all great install questions. We have a couple of guides. We have construction documents that we publish that will show some of these details. And actually today I was working on a fastener calculator tool. So I'm refining this, but the idea is you take your insulation thickness and your total square footage of wall, and the calculator is going to spit out how many screws you need and what length you need based on those things. And so you can input your furring. So there's furring or strapping, people will call it strapping. That is what is going over the insulation. That was wood in some of the last images I showed. That's holding your cladding. And so yes, we want the furring to dive in and sink. We want the fasteners to dive in through the furring and sink about 1.5 inches into framing. And really the requirement is 1 1/4. And then they're calling the tapered head of the screw the additional 1/4 inch. So we say 1.5 inches. So yeah, lost my train of thought for a second there, but more or less, what thickness do I think we need? Code in Connecticut is going to call for an R5 on a 2x6 wall, right? So R5 would be your code minimum. That is not the best building science performance. So if we're concerned about dew point, moisture drive, and all of those things, there's those ratios that I keep referring to. I would ask you to reach out to me and we could talk about your specific project. and make sure, either we're just adhering to code and we're doing the R5 on a 2x6 wall, or we're going to try and mitigate risk of condensation, and then we can do more. And that's what it typically works out to. Code, ironically, on a 2x4 wall is an R13 with R10 on the exterior. That is a clean ratio for mitigating condensation risk. So if you want to go back to 2x4 construction and meet code, you could do it, and it'd be a really killer wall system. Yeah, so that would be R10 for us, would be 2.5 inches of comfort board. The question they also asked about window bucks, I think window bucks are just fine. I see it a lot. I like them. But the window buck is a thermal bridge, right? So it's a vulnerable part of the thermal envelope. And when people are worried about thermal bridging around the buck, they're going to do an inset window. So we call, just between each other at Rockwell, we call the bucked window, we call it an outie, and the inset window on the sheathing plane, we call it an innie. So we have the innie or the outie windows, right? And an innie window is going to have better thermal performance with less thermal bridging. You can get the continuous insulation right up to the window, but you've got to build a return. You've got to build jam extensions when you're doing your trim on an innie window. So we can talk about those details too. Again, reach out anytime. I would encourage, project specific questions, send them over, and let's make sure your project goes off without a hitch.
Awesome. Yeah, and you can use the email that Lewis provided earlier. I'll send it out again to everyone. There it is. And I think that's all the questions we have now. There was another question about AIA, and I will be sending out anybody who provided your AIA number already will be getting a certificate of completion from me in the next day or so. And you'll receive credit and also presentation and the video. So be on the lookout for that.
Awesome. Well, thank you for having me, and thanks to everybody who spent the time out of your day here on a Tuesday to sit and listen to me babble on about Stonewall. It's fun.
Absolutely. Yeah. Thanks for joining us. Much appreciated.
It's a pleasure. All right.
Okay.
Have a great day.
You too. Bye, everybody.
Bye.
Bye.
Thanks so much.